CLI and a cross-platform IDE for C and C++. Download now.
This presentation, the objective is somewhat of a soft sell of genetic programming, because I'm not going to be telling you that genetic programming is something great in 2026, but it is, in my opinion, related in a strong way that is informative of modern artificial intelligence techniques. Okay, I have heard generally the opinion that all artificial intelligence is mostly dead ends, except neural networks is the thing that became really, really dominant and became the synonymous with the whole field, right? There are still a few things that are being done that were classical artificial intelligence and continue to be developed. Unfortunately, I don't think that genetic programming is one of them. So the question arises of why are we going to study this in this time and age, right? The point of view that this presentation espouses is that all genetic programming illuminates contemporary machine learning, ML, and large language model systems because the underlying concepts are the same. Like, for example, the emphasis on searching on a very vast space of possible solutions and the ways to try to traverse that space of potential solutions towards ever better responses is very much still the very same type of endeavor. And with genetic programming, you can inspect the very same things that we're doing today in a vastly different way. For example, it's very, very difficult to ascertain, to track what are the neurons that are important, or the activations or the neural paths that are important that map from a particular input to a particular output. So that learning, that knowledge, or those insights are distributed among all of the weights of the activations in the neural network. In the case of genetic programming, you can see the programs evolving, you can see the substructures emerging that are patterns that are humanly recognizable. We will see one example at the end. And those patterns inform you of more or less why the genetic programming is doing what it is doing or not. Okay, so this is, in my opinion, also illustrative of the benefits that C++ gives us, because there is a genetic programming presents you with the challenge of executing lots of programs with the best performance possible, because the more you can execute programs, or the faster you can execute, and then the more you can execute, and the algorithm can proceed much further than if you had bad performance. All of those things play to the C++ advantages. So we will detail those things when the moment is appropriate. All right. There are the themes concerning genetic programming are very much still central to contemporary artificial intelligence. And what are some of those topics, themes that are still central? Decision under uncertainty, like you don't know what are the consequences of all of the actions that you can take, but you have to take an action, and that's just the meaning of decision under uncertainty, right? And how do you learn from the consequences of actions that you are not characterized completely about what the consequences that those actions can have, etc. Right? Like, imagine, for example, the treatment for a disease. Now that unfortunately I have been sick since yesterday evening, basically a bad case of food poisoning. The the treatments that you have available for a patient, or right? You don't know exactly how a particular patient are going to react to the specifics of the chemicals or the medicines, or the nature of the treatment that the patient specifically can have, and so you can prescribe a combination of different treatments or different medicines to ascertain which are the ones that are doing better, and then you try to figure out why, and then that informs you on your next decision of what seems to be working for that disease, that patient. And that is not necessarily the same thing that you're going to do for a different patient, right? So there is always the challenge of a balance between exploitation of the knowledge that you do have, the knowledge that you have gained from exploring the space of solutions, versus the efforts or resources that you had to devote to continue exploring, because you might be in a local minima in a solution that looks to be better than anything around it, but they can be a much better solution elsewhere that you had to continue exploring, right? And it is very important that what we're talking about are about emergent solutions. And by emergent, I mean the technical concept of the phenomenology of emergent. It doesn't have to do with emergencies. It has to do with that it arises. That are things that the people that were running the system did not anticipate that those solutions were going to have the shape that they had. Like, for example, the whole of the large language models is quite of an enigma, because we can really see how they work. The operation is rather simple. You can describe it without too much effort. But why it works? Why is if you don't accept that large language model exhibit true intelligence, let's say then that perhaps they resemble intelligence, right? Why do they resemble intelligence so effectively if you don't want to accept the claim that they exhibit intelligence? It's not known. To be honest, we don't really know why a text prediction framework, which are the large language models, can do at times, depending on the circumstances, but at times they have been seen performing mathematics, for example. Like and there are mysteries, like why they can do that versus not being able to play a game of chess, because even though they can understand each individual rule, basically all large language models tell you invalid moves in a game of chess quite quickly, right? So those are mysteries that we still don't know. And that's a really important characteristics of all of these things, in which the solutions don't have the nature that a human would come up with. Like all of these artificial intelligence techniques have in common that they come with solutions that a human doing the same work probably would not come up with the same the same approach to solve things. Probably the solutions themselves, if the solutions, for example, are optimal, then they are going to be convergent in terms that a human and a machine will, or an artificial intelligence algorithm will produce exactly the same solution. But the approaches that they follow don't resemble each other at all. And in general, it is not known in advance how the artificial intelligence is going to solve things. Probably you can have some guarantees about the quality of the end solution, but not how the tools are going to arrive to that. Or that is its own research topic. Okay. So all of these things are relevant to things that are completely modern in artificial intelligence, such as reinforcement learning, modern neural networks, all of the panoply of techniques of deep learning that are out there, including large language models. So, in general, it is the same fundamental problems, but with different conceptual tools. Okay, So I am not going to argue in this talk that genetic programming is a competitor approach to the latest AI mechanisms. What we're going to be trying to show is that we're going to gain a different perspective that is informative about everything that is going on in the world regarding, well, not everything, but many aspects of what's going on in the world with artificial intelligence. The C++ angle is that C++ allows us to describe the application domain of whatever scenario that we want to use this technique for with templates, basically. That's what genetic programming boils down to. So you get one repository of knowledge expressed, hopefully only once in the code, from which at compile time, the mechanism of template instantiation creates actual object code that gets a performance nearly what a handcrafted code would give in terms of performance. And another advantage of this is that because you're working at a more abstract level, you are concerning yourself with fewer irrelevant details, then you can write code infrastructure that can be reused across multiple domains. This is one example in the case of genetic programming is that essentially, as the name indicates, we're going to see the definition of genetic programming in a moment, but as you can imagine, it evolves programs, and to evolve programs, it needs to execute those programs to evaluate the fitness that they have, how good a solution those intermediate programs are. And if you are going to be evaluated or executing programs, you're basically, in essence, building virtual machines. And there are known techniques that are applicable to virtual machines, such as just-in-time optimizations. And the thing is that just-in-time optimizations are notoriously hard to get truly right. So genetic programming allows you to write the hard-to-do stuff once that you know is correct and use it multiple times. So it's a big benefit. Another example is that you can capture in an abstract way the algebraic properties of the primitives involved in the programs that you're going to be executing, and profiting from those algebraic programs. What I mean by that is that, for example, if you have the artificial ant, the artificial ant scenario, a problem that we'll describe later, is like the evolution of programs to control a simulated ant. And the simulated ant can do the operation of moving to the left or perhaps moving to the right 90 degrees. So you know that if such a thing would consecutively do 4 rotations of 90 degrees, it's going to end up facing in exactly the same direction. So like the combination of 4 90-degree rotations without any other change to the environment will result in basically a no operation. So you can use the cyclical property of rotations to make that at runtime when a program has a sequence of steps that is 4 rotations in a row, then you can substitute that automatically by a no operation. You just skip and go to the next instruction in the program. This is taking advantage, profiting from the algebraic properties of the primitives that the programs can execute. And also, for example, you can be evolving as programs the ways to compute sophisticated functions, like mapping inputs to outputs. Let's say, for example, John Conway's game of life or whatever, right? How are you going to implement that in terms of programming primitives? There are a variety of algebraic properties that you can take advantage. make the execution of those programs more efficient. All right. So the threshold map for this talk is that we're going to approach genetic programming via a very, very fundamental problem. It's truly, truly important, which is formalized with a name under the banner of the multi-armed bandit. And we're going to even abbreviate that into MAB. We're going to explain what genetic algorithms are, what flavor of genetic algorithms genetic programming are, the parallels between genetic programming and modern artificial intelligence, because the statistical sampling in relation or in proportion to the probability or the fitness of an individual or the probability of an arm in a multi-armed bandit is very frequent. It shows up over and over and over. We're going to describe a hopefully interesting a statistical sampling method. Is called the alias method that converts what would be logarithmic into constant time. We're going to describe a concrete example of a domain application, the Santa Fe Trail, and we're going to do a C++-centric discussion of the challenges and how to solve them. We're not going to be seeing all that much C++ code because that's not the intention. But the implementation is there, and you can see many of the features that we're going to talk about in actual live code. All right, the multi-armed bandit, a really important topic that we need to introduce. Okay, so this is a thought experiment. Before talking about the multi-armed bandit, do you remember, have you ever known that the protocols of Ethernet, like for example, today's Wi-Fi abides by this restriction or this principle. When an Ethernet device attempts to use the communication channel and detects that there is a collision, that it is interfering with another transmitter and the other transmitter is interfering with yourself, the mechanism to deal with that situation is an exponential back off in time, meaning that you're going to wait after seeing one collision, you maybe are going to wait two time slots before trying again. And if you see another collision, then the next time that you try, you're going to double the time that you're going to wait before trying again, which is 4. And then it will be 8 slots and 16 slots and some randomization so that the transmitters don't live lock either, right? So what I want you to observe is that this is a simple scenario of a balancing act between minimizing the delays on retransmitting a package that failed to be transmitted the first time, which we can call like aggressiveness, let's say, and balancing that against the caution that you need to minimize that the collisions reappear. All right. So now let us generalize that problem and introduce a framework that is very important, as I will show you in a moment. Imagine that you are in Las Vegas and you just learned that some hackers hacked some of the slot machines in the casino that you're in. For some reason, you know that the hackers hacked some slot machines in the casino, okay? So that they pay much more than the normal machines would pay. But you don't know which are the machines that they have hacked. Furthermore, they didn't make something really obvious, like all of the hacked machines behave in exactly the same way, and they give you more payoffs in exactly the same way. They made different modifications to different machines. So, because you are not a member of the conspiracy, you just want to profit. You just want to make more money than you otherwise would make. You had to figure out by playing the slot machines, you play in these and see you play it a few times and see more or less what is the statistical profile of the returns that you get playing that machine. And then you go to the next one and try to figure out what is the other statistical profile that the other machine has and so on, right? So you're doing that exploration, let's say, to figure out which are the ones that are hacked, or among the hacked ones, what are the ones that pay the most. But you don't have hard knowledge. You only have a statistical sampling of what the behavior of those machines might be. So you are exploring to try to find the machines that give you a lot of money, and at the same time, you already might have seen some that are giving you more money. So you also want to exploit the knowledge, what you have learned so far. So this is exactly the classical formulation of what ended up being called the multi-armed bandit. And the multi-armed bandit, just to impress upon how important this problem is and how important it is to study it thoroughly, is really important in online advertising, like which ad should be shown to a user of a website, because you might have seen that some particular ad seems to be very effective, but you don't know if there might be a newer ad that is even more effective than the ones that you have been using. So you have to give them a chance to all of the ads that you have in your inventory. And also, even if an ad had performed poorly, perhaps that ad was just unlucky, right? And it is the rational strategy to try to revisit on occasion, once in a while. But of course, if you see that something is very effective, you're going to be giving it more chances, more trials to that ad that seems to be effective. And you're going to be less willing over time to give chances to the ads that were not as successful the first time. And like in the case of the exponential backoff of the Ethernet, the exponentials might be lurking around in there, that some criteria of optimality, depending on the theoretical scenario, might be to increase and decrease the probabilities of selection, or the chances that you give to the different alternatives in an exponential way. This is the same thing of when you are watching Netflix or YouTube. What is YouTube going to recommend to you, or what is the message that Facebook is going to post to your wall, etc., right? The same thing with clinical trials. Like I described earlier, is quite involved. There might be a distribution of effectiveness for particular types of patient that you don't know beforehand. In network routing, for example, if you have a network that is close to congestion, there are routes that continue to give you the opportunity to send messages through them, but you experience problems. So what should be the strategy in general to select which route to carry some particular types of traffic? An algorithm tuning, how you're going to change the parameters of your algorithm so that you get better results. Scientific experimentation, which hypotheses should we allocate resources to test, and the process of how you're going to get to that decision, right? So this is a very classical decision problem. And this type of decision problem allows me to introduce to you more abstract perspective on what genetic algorithms in general are. So you have in genetic algorithms a population of candidate solutions expressed via genomes, and the genomes are bit strings just information that encodes certain properties, certain mechanisms, certain choices in the genome that you can combine with other candidate solutions. Like if you call the candidate solutions individuals, then you can splice some bits, some parts of the specification of one candidate solution and exchange it with some parts of another candidate solution, in the hopes that you're going to be creating synergistic combinations of new characteristics. Which, by the way, let me tell you a famous joke. There is a famous writer of English literature. The name is George Bernard Shaw, that's famous for some aphorisms. And this is an anecdote that this is a joke. Probably this didn't happen, but it's better if it is told as an anecdote. By the way, I should. One moment. Okay. We're doing all right in terms of time. I just made sure that I had my clock. George Bernard Shaw. So, there was an admirer of George Bernard Shaw that was a singer. He was a very beautiful singer. And the singer tells George Bernard Shaw that she admires him a lot and that she has a proposition for him, that she would like for George Bernard Shaw and her to have children. Because imagine how great it would be if the children inherit his intelligence and her beauty, right? It would be a phenomenal combination. And George Bernard Shaw replied, "Oh, I would rather not, because what if they inherit your intelligence and my beauty?" So, the thing about genetic algorithms in general, even the biological evolution of genetic algorithms, is that the suboptimal combinations don't matter. Nature takes care of them because because they are suboptimal, they cannot prosper, right? And what nature does through the process that we normally call natural selection is to allocate resources to the combinations that are better than average. That's why we have interdigital membranes, which is a characteristic that is unique to us. That really tiny difference between the ability to push a little bit more water over some time, it's not trivial, but over some time can become enough of an advantage that the interdigital membranes are prevalent in our species. And well, like I said, if that naivety of a detail eventually becomes important, the suboptimal combinations are displaced until irrelevancy. So the key thing here is that there's a population of candidate solutions that encode characteristics, approaches toward the solution that can be combined randomly and produce new combinations that we don't know whether they're going to be better or worse. There has got to be a process to recombine these characteristics, which, by the way, the people in modern understanding of natural selection, of biological evolution, and genetic algorithms, the agreement is overwhelming that what really matters is the sexual recombination in the case of biology, or the recombination in genetic algorithms. That's why, by the way, most of the successful species in the planet are sexual. There are some species that don't need sexual reproduction, but the success or the popularity or the biomass in sexual species is overwhelmingly much larger than the ones that don't have sex. meaning recombination. Mutation tends to be outright harmful, like the trying of new characteristics via mutation tends to be so harmful that it doesn't pay off in beneficial diversity. So there's that thing of to take into account, but I don't want to make this topic deeper than that. And then you need a mechanism of selection that I later introduced, the apparent oxymoron of artificial natural selection. And I will tell you why that oxymoron that I am proposing it might be justified. All right, so what is genetic programming? It's a flavor of genetic algorithms in which the genomes are trees that represent executable programs. So there is a language that allows you to express a program has a tree. Structured programming, all programs viewed from the perspective of structured programming are trees, right? And the process of recombination is simply the exchange of subtrees. You clip one subtree from one and plug it into the place of a subtree of another. So for that, the more classical or orthodox type of genetic programming is in which all of the nodes in the tree, all of the members in the tree have exactly the same nature, meaning that you can put in there any of the primitives available. But of course, you can hybridize. Like, for example, you can make a genetic programming programs in which there are like control primitives, and they are logical primitives. And the logical primitives plug into, for example, if or while loops. But that's a detail that I've just mentioned, so that you can visualize that your intuition of what that might be matches possibilities and sub flavors of genetic programming. Okay. So now let's see a parallelism between genetic programming and neural networks, for example. So neural networks are learning. They are becoming ever better because there is a mechanism that normally it is the algorithm of backpropagation. No, sorry, what is the name? That mathematically calculates the derivative of the loss function against the activation of the individual weights in the network, and then it moves in the direction that minimizes the loss function. So it is a search. It is an exploration and a search in a space of candidate solutions. And there is some learning going on because we know that it works, right? That you get some practical benefits out of them. The problem with the neural networks is that the knowledge is very, very hard to track. Like, you don't really know what neuron is important or what weight is important in a neural network. In general, you don't know that. You have to do a lot of extra effort to be able to track that. And you would do that for the purposes of research and seeing what's going on and trying to optimize your learning process and so on. But in general, this is truly, truly hard. It's very, very opaque how to have an idea of the knowledge that a neural network has accumulated. In the case of genetic programming, it's not like that. You see individual substructures, subtrees, that are very clear patterns out, and I will show you a little bit later. A pattern or something that you can really see, yes, I can understand why this pattern here is useful. And then you see the genetic programming repeating that pattern all over the genome and making it and re-expressing it in different ways. So it is very resilient to recombination. Because one big difference between programs that are made by humans, but by people, by wetware like us, is that our programs, what we produce in programs, tend to be very, very intolerant of any modification. Like if you change any detail of most programs generated by natural intelligence, they will be extremely fragile. The chances are they're not going to work at all. Well, genetic programming is the programs are exposed to an astounding random sabotage of sexual recombination, of exchanging subtrees one and the other. So eventually, in ways that are very sophisticated and interesting, at least for me to see and understand, the genetic programming programs acquire some resiliency. Like they are reiterative and so on. And by the way, much after I studied genetic programming, I studied the very same thing, but with biological evolution. And our genomes have exactly the same characteristics of things that I have already seen in genetic algorithm and especially genetic programming. How they achieve that resiliency. And like, for example, that most of the genomes in eukaryotes are just basically garbage, just stuff that is there but does nothing. The same thing happens with genetic programming, which begs the question for as to why, right? But all of this is fascinating. Like there are books like Nick Lane's Ascending and Descending, or the 10 most successful traits of life that are quite fascinating. If you want a bibliography for that, please let me know. I caught that bibliography from the slide deck, but I'm going to reintroduce it afterward. Okay. And the reason why I did is that I had to remove a few slides because of the time that I couldn't be with you. So, all right. But I didn't remove anything substantial. All right. The next thing is that the genetic programming by itself has the pedigree of having been a truly successful technique that was used in the real world for non-trivial stuff. In particular, the high watermark is that the researcher that put the most effort into genetic programming, the name is John Cosa. He evolved in his laboratory electronic circuits that were so good that he eventually patented them and licensed them and commercially profited from those inventions. And the claim is that they were evolved via genetic programming. So let's tie back. Genetic programming has a multi-armed bandit, okay? So it is the same thing, but it is a mechanism in which, without knowing the details, you can try different combinations of mechanisms and generate new ones. There is always a balance between giving a chance to mechanisms you don't know, exploration, diversity, versus maximizing the profit from what you do know. This is where I come with the expression artificial natural selection. So my opinion is that nature is the one doing the selection, because you are not going, you are not looking at a program in genetic program and saying, I like this one, so I'm gonna make it combine a lot with other couples to generate lots of descendants of this one program. You're not doing that. You're not doing the actual selection. Nature produces these individuals by randomly recombining them and emerging some mechanisms for the resiliency of the insights that it has already encountered, so that they can combine and continue to be beneficial after recombination. So they had that tolerance to modification of a program. So nature is doing all of that. However, that process is directed by the criteria that you're superimposing on the run of the genetic program. Like, for example, if I don't like that the programs become really, really large because they accumulate a lot of garbage in them, I can make my fitness function something that penalizes a little bit the genomes that are very large. All right. And so what I am asking nature is, please try to give me solutions that not only are resilient to modifications, but they are resilient in a space efficient way. You can do that. Or you can say, you know what, no, I'm not going to make it harder than it already is. And fitness is going to be driven only by the top level criteria that I want. So in that scenario, you see that you are basically not playing the game. You're just stating what the rules of the game are. Therefore, that is natural selection driven by artificial criteria, hence artificial natural selection. I hope you like that. Yeah, I love this type of oxymorons because they compress a lot of knowledge into something memorable. Or I'm deluded that this is one of those examples. You might disagree. All right. So, is genetic programming a gradient descent? I would argue that not really. Like I was telling you that neural network learning critically depend on the differentiability, meaning that there is a system for backpropagation to work. It needs to calculate the derivative of the function if you see the neural network as a function. It doesn't matter that the ReLU function, for example, might not be derivable on zero because what matters are the regions and so on. Technicalities aside, in general, they depend critically on differentiability. So that gradient descent can come to bear. Genetic programming is not like that at all. It samples the solution space on hills, on local minima or local maxima that might be completely disjointed. And you just happen to be exchanging primitives or patterns or subtrees that capture the benefits of some of those local optima, and then get ever better combination synergy, that what I was telling you about. So it is radically different. It is an information-driven exploration of a statistical or stochastical space, but it has inherently different properties. By the way, preparing for this presentation, I learned that there is research now on evolutionary neural networks, in which the reassessment of the weights in the neural network is based on natural artificial selection or artificial natural selection. This is something that was new to me, but of course, it stands to reason that in some scenarios, particularly in some scenarios, and very probably in important ones, the normal backpropagation mechanism is not going to be enough, and you can come up with something better that could give you solutions that wouldn't be found using the classical architecture of neural networks. So we have arrived to a very important part in the whole story about genetic programming, which is the process of selecting pairs of individuals for the purposes of making them participate in the next generation. And this requirement has a lot in common with all of the different applications of the fundamental problem commonly referred to as the multiple or multi-arm bandit problem. So let's say again that you are in Las Vegas and you are using slot machines of those that have an arm that you pull and see what you get in terms of the benefits, s- the randomly selected benefits. And again, let's say that there is someone cheating that has made some machines in such a way that they give you money, but you don't know which they are. So you can be unlucky when you're using the hot machine and it didn't give you anything. But if you try again, eventually it should give you money and more money, right? And it could be that you are not using a machine that has been uh, messed with, but it's just a default one that is just going to make you lose money, right? So you always had to do this trade-off between the evaluation of the exploration of the arms in the multi-arm bandit versus capitalizing, exploiting the information that you already have. It turns out that a very good strategy to accomplish this is to shape the trials, the number of times that you're going to give the chance to one of the choices in an exponential way. And the technicalities aside, we are still going to be requiring something that is very common, which is to be able to select from many different choices. Say that you have 1,000 choices according to the probability of that individual choice. So if I have, for example, I'm going to present you just for the purposes of the demonstration, two different individuals in a population, and then I'm going to call them open hand and closed fist. If open hand has twice the fitness, or twice the fitness has a closed fist, probably you might want to give open hand twice the number of descendants as you give to closed fist. That would reflect that, as far as you know, this guy seems to be a little bit better than this one, or twice as good. So this is going to get selected twice as often as this other one for the purposes of who's going to get descendants in the next generation in the genetic algorithm. All right. If you have that in mind, then what we need is to be able to do that, right? Of given a random number, like a dice or some form of lottery, that's going to give you some random value, to be able to map that random value to any of the different choices, respecting their respective probabilities. And to simplify everything, let's talk about the scale probabilities to the number of elements. Meaning that if an element has, let's say, I don't know, like a tenth of probability of being selected, and there are 1,000 individuals, then the scale would be 1/10 multiplied by 1,000 is going to be 100. That's not very important. What I want you to focus is that there are many things that we can do, right? And for that, I have written a resource after the conference that allows us to do exactly that. Oh, come on. So I wrote in my official GitHub repository, this is already part of the branch master. In SU presentation C++ Online 2026, there is this markdown document of the alias method. And by the way, the reason why I do these things of writing these markdown documents specifically for the conference of C++ Online is because the interaction with the material is eminently online, right? So I think that the people have the opportunity to benefit from several types of content. And my idea is not to actually explain the alias method in such amount of detail that you truly understand everything that there is that it is said in these documents from the presentation itself. My intention is to provide you with the guidance so you can get there. So what we're going to be focusing is on introducing this document and providing the capital insight that allows us to do this. So I have already explained the need that we're trying to recover, right? And one the scenario that we can use to make the intuitions concrete is that yeah, we're going to have, let's say, 4 different individuals in a population, and the probability of selection to participate as parents for individuals of the next generation are going to be respectively 0.2, 0.1, 0.4, and 0.3. If you add all of these together, of course, you get the number 1. So these are probabilities, or satisfy the condition of probabilities. Now, we can also make a cumulative distribution, all right, adding from any position all of the values before it. That will be the cumulative probability function, and represented as an array. And if we do that, then we get this other array. What this array shows you is that the cumulative probability distribution of A is 0.2, A and B 0.3, A, B, and C 0.7, and so on. But now we have like the range from 0 to 1 is split in 4 subranges. So we can draw one element from the range 0 to 1 in floating point. And then we can find, using any strategy to find from that random draw, where does it fall between this cumulative probability function, right? So in my example here in the text, if we get a random draw 0.55, you can see that 0.55 is between B and C, but it's more than B, therefore it is C. And in that regard, if our random draw is 0.55, we are going to be selecting C. If we get a random draw of exactly 0.25, well, that is higher than A and lower than B, then it'll be that we have selected B. So basically you do something like in the case of this scenario, the cumulative probability function is a sorted array. This has to be monotonically increasing, and you then can use binary search. In particular, it would be the first greater than the given random draw. Even if you use the Isinger, that is cache-friendly organization, or any other technique, the fact that this array is sorted will not let you get anything better than ordered an algorithmic complexity in the order of the logarithm in the number of elements. That's of course much better than doing linear scan, but we can do much better than logarithm. Like if we have a population that contains 1 million individuals, then we still need around 20 binary search steps to arrive to the element being selected, right? The efficient solution that implies a solution for this type of random draw that is applicable to any scenario of the multiple arm bandit problem. That's why it makes it important, is that you can, for the cost of linear in the number of elements setting up, which you cannot do better than that, because if you had to take into account all of the probabilities in the selection space that you want to check, then you had to go over each one of them. That's linear, right? So it cannot be done better than linear. And the lookup is constant time. It is as cheap, literally has indexed into arrays. We will see in the code that that is indeed the case. That approach that I'm going to tell you the insight is called the alias method. This is something that has its own its own Wikipedia page, and as part of the preparation to this presentation, I went and checked on the C++ implementation of linked via the Wikipedia. And what I can say about this implementation is that it does things like, for example, baking in what is the distributions needed for the purposes of the random selection. It commits for no good reason to a particular random number generation pseudo random number generator. It needs a random device. So all of these, the randomness ought to be provided at the call sites, just for the purposes of showing you what I mean. Um, I wonder, maybe here? I don't remember where I put. Yes, of course. It has its um, alias table. As I am. Okay. So the implementation of the alias table that I made separates very cleanly all of the things that are properly the alias method from the randomness and all those things. So I believe that only at the very end, it is when the randomness is taken into account. This is things that, of course, the user could maintain, and that's much better, right? Because it is not committed to any particular random device or generator or anything. It just needs a uniform real distribution. By the way, there is also the efficiency that I only need one random draw, the other implementation requires two. Okay, going back to the explanation of what the alias method actually is. The general idea is if we come back to these probabilities that I selected in here, 2, 1, 4, and 3, then we can sort of capture that that set of probabilities in this string. Let's say that we have a minimum tick size of 0.1 of probability. So the probability of A being selected is twice that. So we're going to repeat A 2 times. B is only a tenth, so it is going to be there only one time. C has a probability of 0.4, so it is 4 times 0.1. So I repeat it 4 times, and D 3 times, right? So now you have a total of 10 elements. Let's say that you have an array that contains the index of each of the individual alternatives. So I can create a random draw, an integer random draw between 0 and 10, excluding 10, and that will give me the index. And by indexing that this array, it's going to tell us what is the element that was selected, right? So this is very good because this is the strategy that we will try to follow. We request a random draw and we index into an array, and that tells us what is the element that we got. However, what I did here, if you take into account, there are two properties that you cannot achieve, you cannot take for granted. The property number one is that there is, has in the case of the initial probabilities, a minimum tick size, in this particular case is 0.1. from which all of the individual probabilities are an integer multiple of that tick size. And even if you had that, like let's say, for example, that the tick size would be not 0.1, but 0.01, then you would need to create an array of 100 elements, right? So making the array has fine-grained enough, has to support that tick size, could require arbitrarily many positions in the array. So you just cannot generalize naively, right? So the alias method, what it does is to give us the opportunity of accomplishing the same thing by an interesting idea, which is we're going to have an array of 4 elements. Then in the concrete case that we have here, or n elements if in the general case. And if you think about it, from all of the different choices, because these are probabilities they had to add up to 1, there are going to be some for which one entire bucket would represent more probability than what they actually have. Like in this particular case, if we have from four positions, we would have an array of 4 elements. And then if you see those 4 elements has an spawn, each bucket, each member of the array would represent a quarter of 1 or 0.25, because there are 4 elements, a quarter of the total range of probabilities, right? So if you give a whole bucket, a whole element in the array to A, then you will be overstating its probability, because the true probability of selection of A is 0.2, and you would be giving it a quarter, which is 0.25. So what do you do in that case? Well, it's very simple. For index A, you're going to write the number 0.2, which is its true probability. And implicitly, there will be a remaining 0.05 that is not used yet. And that's where the alias comes from. You're going to give that 0.05 to some other element in the set of different choices that currently requires more than a simple slot in the array. Again, because these are probabilities, there are going to be some that are up to the size of a slot in the array, and the counterparts, which are those that require at least one slot in the array. And we can call them the smalls and the largest. So the algorithm works by pairing one small and one large in a way in which it writes the true probability of the small to the first array, that we are going to call it the array of probabilities. And the remainder would be implicitly assigned to the member of the largest that is being paired. In this particular scenario, arbitrarily, I chose D. And the aliasing, and hence the name, is indicated by having a second array that you are going to call them the aliases, in which for the index A in the aliases array is going to be written the index of D. And in this way, you can indicate that this bit of probability that was left in this bucket that you assigned to a small was given to a large element. So what is it that we do when we do sampling is to draw a floating point number uniformly from the semi-open interval 0 to n, and do what I'm going to show you in the code, which is this is a uniform real distribution that this is implicit in the contract, must go from 0 to n, excluding n. And So that number has an integer part, and that's what is going to give us the index to consult it in the table, and it's going to have a fractional part. So if the fractional part is less than the front array, the probabilities table, then you know that that belongs to that index into the table, and therefore you just return the index. If it is that fraction is larger than the threshold intra bucket, then you're gonna select the alias for that particular index. Okay, so we are almost done with. So this is something that I tried to replicate in the slide deck. The slide deck, again, this is material for a presentation. So I am only attempting to provide guidance at the level of the slide deck, because the details ought to reside in different places for your interest. When you want to visit those materials, I want to know the details and understand things in detail. So scale probability of a small element, alias to a large element. And so we see here a simple representation of the code, then how it would look like. And this is an important part, because this is the place where you classify the initial probabilities into the two partitions of those that are small and those that are large. And it's very simple. You just multiply the probability of at index I by the total number of elements in the array, and then determine whether that is greater than or less than the unit. And that's what's going to decide whether it's a small or large. So again, this is the relative probability, right? So if the relative probability is less than the unit, it is a small. This is the core of the setup loop. When you have not either, you must have both elements in the small partition and elements in the large partition. Then you pick one small, it doesn't matter which, by implementation convenience, we're going to get the one at the end of the collection. You pair them and do the dance that I was telling you of whether you're going to be aliasing or not. And you remove the elements from their categories. That's why you do the pop backs. And also for the big, you might have given it enough probability that it used to be a large element and now it is not a large element. So you put the remainder of the probability that it needs into the small set, or it might remain a large, so you reintroduce it. Okay, that's the core of the algorithms for the construction of the alias table. And like I said, there is an implementation that I like. It's much cleaner than other publicly available. Now we have the opportunity to visit, for example, the let's see 1 minute how we're doing. The demo of the Santa Fe artificial ant trail. Let's do that. So this is a very famous problem in genetic programming. This is like a foundational. And let's see this in better detail. What we see in blue in this picture is a grid. So we have a grid, and in the grid, The blue parts are pellets of food, and we're gonna build and make evolve programs that control a simulated ant, an artificial ant, hopefully so that it would the program that controls that ant is gonna allow the ant to traverse the entirety of the trail. See that it begins with a contiguous set of food pellets, and here's the first gap. So the program must somehow be able to skip this gap and continue. And then the gap is of two cells, and then gaps happen in a corner. Like I think this is the first gap that happens in a corner, and so on. So it is a challenging thing that I can um, uh, recommend you to try to see it. And what are the programming primitives that we have available to implement this? Very simple. We go here to our code and artificial ant environment, I think. So there are several primitives that we can use, and we can get them from the functions that implement those primitives, like flesh out what they do. One is to turn left unconditionally, to turn right, to move one step ahead, to move, not to move, sorry. This IFA is the abbreviation for if there is food ahead. And this is the first primitive that is not a terminal. This is a non-terminal in the programming language. This, in the way that I have modeled in this code, if food ahead only has one descendant, a sub-tree, one sub-tree, not more than one sub-tree. For the case of what you want the ant to do, if it finds that the sensor says that there is food ahead. And that's why the implementation is you query to the environment in the way that I'm looking right now. Do I have food in front of me? If that is the case, then I will go and evaluate the subtree, which is the beginning of my list of descendants. But the beginning of the list of descendants is the entirety of the list of descendants. Proc2 is just to execute unconditionally two descendants. And proc3 is to unconditionally execute three descendants. So let me show you a very little demo that I made in which there is this program, okay? This at the top level is just a combination of two subtrees. This will be one of the two subtrees. If there is food ahead, then move, because why not, right? If you're looking at food, then why wouldn't you move to just eat that food, right? If food ahead, move. And unconditionally turn right. So this very simple program is a fragment, like one of those that I mentioned to you a moment ago that, well, not a moment ago actually, but in the previous presentation, that appears over and over and over when you see the population evolving. And this is how, if you look at it as a program, how it would evolve. So what I put here in the courses library is a representation of the same trail that we saw on the Wikipedia page. And the arrow indicates what is the direction that the ant is facing in. And so you see that it is turning to the left unless there is food. And if there is food, then it just goes and eats it. And that program is too simple to overcome this challenge. But of course, we ought to expect something like that, right? Okay. So This is the Santa Fe tree problem is a foundational thing that if your implementation of genetic programming works, it would be able to deal with this very easily, like with only 500 elements. The population of 500 would be enough and stuff like that. And you can also, of course, make this trail, you can make a generator of grids in the style of this grid with challenges that are progressively harder or maybe not even progressively harder, and see how the artificial ants, the programs for the artificial ants evolve in a much tougher, in which they cannot just learn this particular trail, but they need to learn any trail. And again, you see that particles like the one that I showed you a moment ago appear repetitively. All right. So um, the one of the things that I said is that it is truly important to do um, exploit that when we are going to be evaluating programs, we are very probably going to represent those programs specifically as trees. And trees have this property called self-similarity, which what you're going to be doing at each level is very, very similar to what you do at the immediately next level, either a deeper level of traversing of the tree or closer to the root. And this is an example in which recursion, the programming technique of calling a function from within itself, is very natural and powerful and convenient to represent what you're doing, right? And this document tells you that there is a problem with recursion that we need to be aware. By the way, this is not something that other programming languages that support recursion explicitly do any better. This is a problem that we experience in C and C++ in a very direct way that other languages do worse, even languages that have explicit support for recursion. And so, what is it that we have here? That when you recur, it can be that you're calling a recursive function from more than one place within the function. So you need to somehow remember different places in the code where you're going to continue when you come back from the recursion. Those are called continuations. And how do you represent continuations in C++? Well, in the case of truly recursive formulations, the generated assembler is just going to push to the stack the return address, which is really, really cheap. And the processors and the application binary interfaces are made to make that extremely performant. There is a problem, which is that when you do a proper recursion at the application binary interface, you hit two problems. The Goldilocks problem, in which the application binary interface defines a one size fits all binary interface again of how much space the stack must reserve, what registers are going to be preserved in the function call, what registers must be saved, what so you can have the problem that for your particular scenario is overkill the amount of space that you save in the stack, the number of registers, or perhaps you need a larger context and what the application binary interface requires you to save is too few of them. So all of this is inefficiency. It's a Goldilocks problem. Like some scenarios would be too much, some other scenarios would be too little. And as of this era, like around the middle 2020s,
jumping into a recursion frequently works as a compiler optimizer barrier. That's why it is profitable very often to convert a recursive specification into an iterative specification by you creating your own stack, because you don't have a proper function call that needs to say too much or too little into the stack. And also, the compiler doesn't lose the opportunity to optimize from iteration to the next iteration. And I can submit to you that my implementation of Quicksort in this very sub repository is an example that takes advantage of the manual reconstruction of creating an explicit stack to keep within an iterative space that it is highly performant. And I control, for example, that the maximum recursion depth is going to be of 64 elements, because the nature of Quicksort is that if you recur only to the smaller partition, the partition that has the fewest elements, and iterate on the partition that contains the larger amount of elements, then for an input that must have at most 2 to the power of 64 elements, you're not going to have more than 64 levels of recursion. And 64 levels of recursion in a stack that only has the markers for the beginning and the end of the range is so little space that you can just use it locally as a local array and get done with it. And you still have the guarantee that you're not going to Stack Overflow. Quicksort, on the other hand, if you are writing in a naive way, even a good implementation of Quicksort might Stack Overflow. What is it that you do when you cannot get away with a solution to having to remember when you're going to be continuing? Because the problem is that in C or C++, well, in C, and therefore this problem is inherited from C and C++, you cannot treat what you're going to continue as a proper value so that you can put it in your own explicit stack that you have devised to support the recursion. Because if you put what you're going to be continuing as a function pointer, then you're already defeating what we wanted to accomplish with the iterative formulation, right? Of not having an optimization barrier and not having the Goldilocks problem of the application binary interface. So that's not an option. And what you do typically is that you define continuation enumeration type, in which you're going to indicate all of the places where the recursion can return to, and push to the stack what is going to be done upon coming back from the recursion, and articulate that has a switch on the continuation of the current frame and a bunch of cases that represent the things that could be continuing afterward. The problem with this transformation is that the performance gets lost, because switch statements get lowered to indirect jumps. And indirect jumps have 10, 100 times worse performance than jumping to the return address in the current stack frame. Furthermore, indirect jumps are also optimized barriers. So we are back to not having something that satisfies us in that regard. Okay. We are getting very close to the end of the presentation. The things that I needed to tell you for well, maybe we can sees the code for that, because it's an interesting thing. Yeah, so because I want to be able to have optimization techniques in which I modulate the recursion by perhaps substituting exactly the function that I am recurring by not the generic, the most general recursive function, but one that takes into account, for example, if I have a scenario in which I know for a fact that the artificial ant has consumed all of the food in the environment, then I can create an evaluation function that is going to take that as an optimization opportunity in which checks, for example, of whether there is a pellet of food in the environment are going to return unconditionally false or true or whatever the case might be, right? So I want to be able to modulate what is the recursion that I'm going to be doing. So I want to pass to a recursive function the function pointer to itself. But you cannot do that because if you think about it, and this was something that people during the questions and answers at the conference were very interested about, you would have to specify a recursive function pointer type. And that simply is not possible. So I use this idiom that is a well-known idiom of converting a recursive function pointer into a void pointer and recovering the true signature via a reinterpret cast. And by the way, this is not an evil reinterpret cast, because what you are referring to through the void pointer is always something that initially had the type that you wanted. And so this is a very straightforward implementation of evaluation. It uses the functions that I showed you at the beginning. And the invocation of the recursive function is rf of recursive function. So nothing something particularly strange in here. However, I broke my brain to be able to make an iterative formulation of evaluation. This is what I came up with. So I sidestepped the problem of the continuation by making the ad hoc observation that in the set of operations that I have of turn right and left, in which I only have if foot ahead, proc2 and proc3, none of these non-terminals in the programming language have interplay between its descendants. It is just unconditionally executing at most one descendant, and the count of descendants is known ahead of time. Then I didn't have the problem that I was telling you about of a recursion that might come back to more than one possible continuation. So I could get away with this formulation that is really, really efficient. But here I have all the problems, and I don't have the detail is too deep to tell you what's the problem with this. And it still, even if it works, has a nasty problem, which is this was done only because ad hoc properties of the application domain that I was using. Okay, so the last thing in our presentation is concerning optimizations of the kind that a just-in-time compiler might do. And we're just gonna take them from the slide. Like there's a simple example. In the artificial ant domain, if you turn to the left and immediately turn to the right, that's a pattern that can be recognized as a no-go. We can also take advantage of the cyclical nature of what turn left and turn right means. So combinations of several turn lefts end up becoming a turn right and so on. So what do we have to do to take advantage of this? As the slides say, we can form a canonical representation of repeated invocations of associative operators. And you can also have a semantics layer that has the pattern matching into it that makes transformations of code that is more involved to be computed into abbreviations that are shorter and more small. And this is exactly the same thing as what runtimes for programming languages such as Java do of combining formal properties and execution profile statistics to transform the code on the fly towards something that takes less effort to compute. Now, this is something that hugely improves the performance of a genetic programming engine running under C++, but it has the problem that all of these transformations are really complicated. But what we're doing is basically to take advantage of algebra and mathematical properties to do transformations that are cheap and consequential in terms of performance or latencies. Very well. So I explained to you the problem. The solution would be that in C++ you would have the opportunity to simulate the equivalent of going into a return address from the current stack frame, and there are several choices to do that. In here, I have a hunch, something that I'm going to be researching, that coroutines, because coroutines are sort of ad hoc function call binary interfaces. Like they don't have to abide by the one and only platform application binary interface, but they can make their own ad hoc decision on driven by the compiler optimizer of which registers to save to the stack or not. The coroutine resumption and continuation, suspension and continuation framework. All of that is programmer supplied. So in principle, you could have something more efficient, and so it's a qualitative thing to be explored. And another thing is that the language might allow you to compute destination addresses for the code and say, I want to run to that thing that I already pre-computed, and it'll be different to indirect jumps in a couple of critical ways, but that's at least it seems too detailed. Okay, so we can go back to the slide deck. This is the example that I was telling you about, and I would like to tell you that, for example, this book has been one of the greatest reads that I've had in the last 10 years, perhaps. It is called Life Ascending: The 10 Great Inventions of Evolution. And this is very informative. So most people learn about the properties of evolution because of biology, but my approach was exactly the opposite. I learned about evolution because of genetic algorithms, and I got fascinated by how much biology uh, discovered on its own the techniques that make genetic algorithms efficient. By the way, I don't know if I said it before, but genetic algorithms continue to be a valid tool in the toolbox for it's a legitimate artificial intelligence technique that continues to be used. It is just not as important as neural networks. And it has been a pleasure to cover the gap that the presentation had because of my momentary disease. And that's going to end it's going to end the presentation for us. What happens that I cannot? Thank you very much for your attention.